six-sided die and record the sum, which sums have the lowest theoretical probability of occurring? And so who has an answer for that? Which sums would be the least likely? Gary? Okay, 12 is one of them. There's another one that has the exact same theoretical probability. Lane? 2. Getting a 2, because that only occurs with a 1 and a 1, or getting a 12. And so the sums that would have the lowest theoretical probability would be a 12. It's not working the way, there we go. Or, I put 1, or a 2. Which sum has the highest theoretical probability of occurring? Shannon? A 7. What did you find? How many options or outcomes were there to get 7? So you could get the 1 and the 6, right? Is that it, right? 1, 2, 3, 4, 5. So 6 out of 36 chance of getting a 7. And that was the one that had the most likely option, or in this case, the highest theoretical probability of occurring. All right, which is kind of interesting. Yesterday, you guys rolled 2 dice and you recorded the sums. And so I'm going to show you the results of what happened from that. I think I have it on here somewhere. This dot plot represents all of the sums combined from, I took 10 of your papers. I just wanted to make it an even 100. And there were 4 of you who had a sum of 12. So not 4 of you, sorry, 4 trials, 4 rolls. There was a sum of 12. There were, we got 11 4 times, 10, however many times this is, 9 this many times. And you can see that there was only 1 2. There were 5 3s and so on. So that's what each dot here represents rolling the dice 1 time. And I just combined 100 of you guys' trials together. So on here what you can see is experimental probability. 7 and 8 were actually equally likely in our experiment that we did as a class. Okay, so experimental probability and theoretical probability it is possible that they're the same, but most of the time you get different values. Does that make sense? Okay. Events, and then finding probabilities of those events. So I want to know what's the chance that I get a 7, and then that I get an odd number the next time. Or that I get a 2, and then the next time I get a 1. Something like that. And then also finding conditional probabilities. So we'll talk more about those when they come up. So I want you to think about, in your own words, what's the difference between independent events and dependent events from what I just talked about? Who thinks they could put it into words? What do you think, Keegan?
Independent is one specific draw.
Okay.
And then dependent is the whole experiment.
Okay, so not quite. Because independent can still be multiple things happening. Like, I want to draw a 5, and then a 5, and then a 5.
Is that more like...
Right? Or, I guess it doesn't make sense. Well, it would. I want to draw a 5 from here, put it back. I want to draw a 5 again, and I want to draw a 5. So it's still a complicated process, sort of. I still want 3 events to happen, put together as one event, kind of. But what is it that's different between independent and dependent? I want to try to just get it in your own words. Yeah.
Independent is it isn't changed by a different experiment or event, but the dependent, it matters.
Okay. Yeah. Shannon, what were you going to say?
Like the independent, it stays constant every time you redo it, and the dependent, something is being changed to it, which changes your outcome.
Okay. Audrey?
When it's drawn the first time, it doesn't change anything that happens later on.
Okay, so when your first event does not change something that happens later, then you're independent. Okay. Okay, so what occurs first does not affect what occurs next. Is that what you're saying? And I think that's a good way to say it. It's less complicated than the book definition, so I like it. What occurs first does not affect what occurs next, whereas in dependent, what occurs first affects what occurs next. And we're not going to be super picky about proving this. It's just an understanding of, can you explain whether events are independent or dependent? And so we're just going to look at this first example 1. It says a bag contains 6 pieces of paper. So here's my 6 pieces of paper. They're not in a bag. Numbered 1 through 6. A student randomly selects a piece of paper and replaces it, and then randomly selects another piece of paper. Use a sample space. We're going to cross that part out. In your book, they make you kind of prove that events are independent or dependent, and we're not really doing that. So we're just going to determine whether randomly selecting a 5 first and then randomly selecting an odd number second are independent events. So what is the chance that I choose a 5 first? 1 out of 6. If I put the 5 back, does it affect the chance that I get an odd number next? No. And so these are independent events. And we're not going to even write a whole description of why, because I think we've talked about this drawing cards one a few times. But what I want to show you is, it says example 2, what if in the previous example the paper was not replaced? So I draw out the 5. So before I do that, let's think about the first one again. Chance of getting the 5 first was 1 in 6. Is that correct? What's the chance of getting an odd number if I did put the 5 back? Yeah, there's a 1. Where's the 1? There's a 1, a 3, and a 5. So there's 3 odd numbers out of 6. So 3 out of 6. We're going to learn in a minute a formula for this. If I want both of these events to happen, we multiply their individual probabilities. And so to get the 5 first and then get the odd number, we multiply across. 1 times 3 is 3. 6 times 6 is 36. And we get 1/12, technically, for our probability. Or just 3 over 36. But what if I chose the 5 out first? Oh, that chance is still 1/6, right? But now I want an odd number, and I don't have the 5 in there anymore. How many odd numbers are in there, Cody? 2/5. And so the overall probability of this large event happening, this two things happening, is going to be a 2 on the top, a 30 on the bottom, or 1/15. And so the chance of this happening has changed because of the fact that I've changed the way I've done the experiment. Okay? And so in example 2, this would be considered dependent. Whenever you're just thinking about drawing things out of a bag, it's really obvious when events are dependent, because if you draw something out and you don't put it back, it's obviously depending on the other. What's not as always obvious to people is, let's say I'm talking about this classroom. I'm going to pick 2 people. Those 2 people are just going to get A's. That'd be nice, right? You don't have to do anything. I'm just going to give you an A. What is the chance that I pick 2 females? Okay. That is technically dependent events because I pick a female. I don't get to pick them twice, right? So I pick the female, they're technically removed, and then picking the second female. Okay? And those are dependent events then. You just don't think about it as 2 things. When I say I'm going to pick 2 females, but it is technically picking a female and then followed by picking a female. Okay? And that would be considered dependent events. Now when we play that game with the cards, and I shuffle through them and I pick a name out, and let's say it was Hank's turn, I put that card back in, and I shuffle him again. Every time I call a name, he has an equal chance, he has a chance of being chosen for that. It doesn't affect, if he was chosen once already, he could very well likely be chosen again. Now, sometimes I put the names to the bottom of the pile so that doesn't happen, and then it's dependent events. Okay. All right, just to save time. All right, up at the top of your paper, if your events are independent, then the probability of getting A and B to occur is the same as probability of A multiplied by probability of B. We just saw that happen. And while we're at it, let's write down the formula for dependent, although there's going to be some notation that's we haven't mentioned yet. The probability of A and B occurring if we have dependent events is still the probability of A, but then you don't just multiply it by the random probability of what B would be alone. It's the probability of B given that A has already occurred. And so this is new notation for you.
Is that a minus? Or is that count one?
These are multiply. So what this means is the probability of B given that A has occurred. And that's what's called a conditional probability, which we'll be actually just calculating conditional probabilities on their own a little bit later.